and welcome to the asynchronous lesson for Calculus 2 on, this time, volumes of solids of revolution. So before we get into the new material, I want to review what we went over earlier about the volume of solids of cross sections. So the main parts of this come from the intro problems from the previous lesson. So those are the idea of slabs, whereby we can find the volume based on the area of one of the faces multiplied by the thickness. So if it's a cylindrical slab, which will come up a lot of times later today, the area would be pi r squared, and then multiply that by the thickness to find the volume. If it is a rectangular slab, the area would be length times width, and then multiply that by the thickness to get the volume. Another thing that will come up in the second part of today is the idea of area between, where we will take the curve on top minus the bottom if we're going vertically, or if we're going horizontally, we'll take what's on the right minus what's on the left. So that's a little bit of background. We are going to continue reviewing it by just reminding that when we're finding the volume of solids of cross sections, what we were doing is we were creating a slab, which was whatever area it was dx, and then we were integrating. And again, that's going to come up. However, now we are going to be talking about rotating a curve around the axis, which is going to modify it just slightly. Now, what is different about this is we are going to form a three-dimensional shape by taking a two-dimensional curve and rotating it around one of the axes. So what this is going to do is this is now going to make our cross sections cylinders, because again, if we rotate something, it's going to form a circle that's rotated uniformly. And then if we add thickness, well, if we add thickness to a circle, then that's going to form a cylinder. And so what that's going to mean is that, similar to the intro problem from the previous lesson, we are going to have solids with a volume of pi r squared times the thickness. So an example of finding the volume of a solid rotation is when we're rotating the solid formed by y equals square root of x from 0 to 9 on the x-axis or around the x-axis. If we rotate this around, it will create cylinders which have a thickness of dx. Because we know that if we look at this, we have the thickness being right here along the x-axis, which is dx. Now, in this case, the radius is going to be y, which we notice y is equal to the square root of x. So the volume of our disk is going to be dv is equal to pi r squared dx. Because again, we're talking about circular cross sections. And the radius in this case is y equal to square root x. And you notice we have dx here, so we want the variable to agree, meaning we're going to write square root x. Now, to find the volume, all we need to do is we need to integrate that. So, by the way, square root of x squared is just x. And so we calculate the integral from 0 to 9 of pi x dx, which I remind you, you can use Desmos for. And that ends up being 81 over 2 pi. And that's all we have to do. A slightly more complicated version of this is when we are given the area between two functions, we're rotating that around an axis. So in this case, we are rotating the area between y equals negative x squared plus 4 and y equals negative x plus 2 around the x-axis. So in this case, a general sketch of the area reveals concentric circles with a gap in the middle. We also note that we have a thickness along the x-axis, and so this results in dx being our thickness. As for the area, the area is formed by taking the area of the outer circle minus the area of the inner circle. So the outer circle is formed by the parabola y equals negative x squared plus 4. So negative x squared plus 4 is the radius of our outer circle. The radius of our inner circle is y equals negative x plus 2. So subtracting those areas and multiplying by the thickness gives the volume of what we call a washer, which is a disk with a hole in it, of dV is equal to pi outer radius squared minus pi inner radius squared dx. To find the volume, all we do is we integrate this. So we have the volume being the integral from -1 to 2, which are the x values of the intersections of the curves, of pi outer radius squared minus inner radius squared. Please note that I moved the pi out front using factoring. You don't need to do this, however, it does save writing. And again, for this unit, you can use Desmos to calculate the integral, and doing so gives a final answer of 108/5 times pi. The last case that we will talk about for right now is when instead of rotating around the x-axis, we rotate around the y-axis. A good first point on all these is to sketch the general idea of what we're going over. So rotating around the y-axis will give a flat circle as opposed to a vertical circle. And now a key difference is that now our thickness is up and down, so that's dy instead of dx. So our radius will be along the x-axis. Our radius will be along the x-axis, so our radius will actually be x, and our thickness is dy. So multiplying pi r squared times dy gives us the thickness of a slab. Now we note that our variable is y, so we're actually going to have to solve for x, because our radius is x and yet we have dy, which if we want to solve y equals x cubed for x, we have to take the cube root of each side, which gives x equals the cube root of y. And since x is our radius, that means that's equivalent to the cube root of y, which then agrees with the dy. From there, all we do to find our volume is we just integrate the resulting expression. So we have the integral from 0 to 8, which are the y values of the region that we're given, of pi and then cube root of y squared dy. We can then use Desmos to integrate, and we get 96/5 pi. That is all for this lesson. Thank you for watching. Have a great day.